since in Santander in New Zealand and back in Europe, enjoying that a lot, I think. But he's at the Institute of Sciences de Mar, so the Sea Research Institute in Barcelona, and he will tell us about how we're going to open this black box of AI and coastal modeling.
Thank you. I actually changed the title a little bit so that I can better fit with the overall aim of the workshop. That's completely irrelevant, the title. What is important is why I'm here. I'm here because I want to celebrate an incredible scientist, fantastic modeler, but also a human being that has taught us that you can do incredible science while enjoying playing the saxophone and the clarinet. For this reason, you will see quite a number of analogies with music, because I wanted to make this a real celebration of a scientist I admire. AI, let's get started. AI is the perfect place, the perfect world for the problems that we have. We try to model, to predict, to understand the system that is intrinsically very nonlinear, multidimensional. We have observations that are noisy, so it seems like we have all the ingredients to match with the AI world. At the same time, I have to say we have to be aware that this is a dangerous path, because when we hear about the incredible results of AI, usually we're talking about data sets that are petabytes. Sometimes we apply AI and we have 80 points. So there is quite a difference, and that means that it can be dangerous. What I want to do today is really have a look at what's been happening in the AI world, discuss machine learning techniques. I call them more shallow learning, how now we are all into deep learning, and then I want to spend a couple of minutes to discuss AI agents, because I believe AI agents will change our world, will change the research world. So we should spend a little bit of attention on that. Now, you will see this image for quite a bit throughout the presentation. Let's start with our analogy between music and machine learning, or shallow learning. So all those techniques like genetic programming, random forests, simple artificial neural networks. Well, what is happening with those techniques, with this approach, is that we learn patterns. It's like we play a lot of music of Coltrane, Coleman Hawkins, Lester Young, and the algorithms learn some of the patterns that occur in the music. They struggle to do really new things. They're very good at reproducing these patterns. But that's what this is. And in many ways, I consider at this point this the past, because all these techniques are optimization techniques, search techniques. Great start, but we're at a stage where there is a lot more. I will tell you about this other musician as we go. For now, let's just have an example of what machine learning, shallow learning is like. And I want to use one technique that some results from one technique that I've always liked over the years. It's not the most powerful. Genetic programming is not the most powerful of the shallow learning techniques, but it has a huge advantage. It produces formulas, which in this case, for example, they are dimensionally challenging, but formulas that you can look at. The operator, the scientist, is still critical in this process, because you have to decide whether the formula makes sense or not. In this case, we applied it to the prediction of swash. Here you have measurements, here you have predictions from two different models produced through genetic programming, and the most cited paper from Stockton et al. Now, what we can see here is that, well, with genetic programming, we can definitely decrease the spread compared to the Stockton model, but it's yeah, there's still some problems, especially when we get to a stream. We do really well down here, where nobody cares really, because you want to know where the swash is big for flooding. And with the extremes, yeah, we do better than Stockton, but it's not great. In any case, it is an improvement, so why not using it? We should do that. And as we get more data, the advantage of these techniques is that you can just quickly retrain, produce a new model that will be always a better evolution. So that's a great point about these models. You get new data, retrain, get a better model. I also want to make another point with respect to this work and to the use of machine learning. We always say, I say it too, machine learning cannot generalize. You should not use it over unseen sites, because it could go crazy. What is now called hallucinations. Hallucinations, they don't really apply, I think, to shallow learning, but let's use the term that has become common. Here what we did is we used the models that you've seen earlier on that were trained and tested on the same dataset over which Stockton was developed, and then we applied the model to unseen data. 2 beaches on New Zealand, one on the west coast, one on the east coast, and 1 beach in France. And here we can see that actually, despite the general idea that you cannot generalize, well, we actually do a lot better than Stockton. Now, I'm not saying that, oh, then we can generalize. No, what I'm saying is that what I learned from using machine learning is that every data set is different. So you cannot make statements without actually checking. Because in this case, actually it's generalizing better than the model we are all using, the Stockton one. Okay, we have a number of those techniques. We have a number of studies where we get data sets. We improve the data sets through those techniques. They work very well. We write nice papers. But that's the past. These are optimization techniques, search techniques. There is a lot more to machine learning. So let's go back to our analogy with music, and let's move towards deep learning. Now, things here are getting interesting, because not only that our virtual musician can learn patterns, but actually begins to understand patterns, can generate new music. It's quite a difference the moment we move to deep learning, because we can almost be creative. We can handle temporal sequences. We can generate new music that is coherent, not just repetition of patterns. Okay, this is a big change. This is a huge change, in fact. For this reason, I want to spend a little bit of time telling you about some of the techniques that have now become common. At the base of a lot of deep learning algorithms, there's artificial neural networks, just stacked up in a smart way, one on top of the other, several of those, multiple layers involving several neural networks. And some models are now really widely used. The convolutional neural networks, they started to generate images, amazing at generate images. And I think one nice thing that we did in the nearshore was to start using them also for temporal representation of changes. A lot of examples of those techniques. Then we have recurrent neural networks. Gerben Ruesting started this a lot of years ago. At this point, I shouldn't say a lot, some years ago. They're fantastic for sequential type of data, and they were not really good until we actually developed long short-term memory algorithm. Then that's when we started getting really good at getting temporal dependencies in the data. So both techniques, convolutions, LSTMs, are very common. And then we moved on to transformers. Transformers, we all use transformers because we all use those large language models like ChatGPT, and the base for that is transformers. And then there is another category that is growing more and more, and is the generative models. Generative adversarial networks, they're really good, and they're used to create new things. Now, here we need a lot of data. We need a lot of data because the key part of the deep learning is trying to understand from data what are the key features of the data. Once you get the key features, once you get the features out, this is what is used to generate predictions. And they work amazing. The step from shallow learning to deep learning has been huge. Nowadays, we almost all tend to use deep learning in one way or another. And now I show you one example of a deep learning algorithm where we actually decided to combine, this was PhD student Eduardo Gomez de la Peña in New Zealand. He decided to not use just convolutional neural networks or long short-term memory, but to combine the two. It's like a saxophone meeting a clarinet. They get together and says, hey, I'm great at understanding images. I'm great at understanding sequences. Let's play together. Let's build the model together. We extract from data both spatial and temporal features, and there we go. We do great forecasts. We play great music. So let's have a look a little bit at this result. This is an unpublished result when Eduardo went to work with Sean Bituzek to look at Ocean Beach. Here's all the wave data, and here's some of the results. We had over 20 years of data to train the model. Here what you're seeing is just the testing, so the last 5 years of data. Time is on this axis. On the vertical you have the shoreline displacement. The yellow crosses are shoreline position derived from satellite. The red crosses are actually observations from the field, so we can see that the satellite does a good job. Well done to Voss and co-authors for giving the community this amazing tool. Still, the best thing is to probably smooth out all the observations we have and then trying to predict. And that's the result of our algorithm that combines convolutions and long short-term memory. It works pretty well. It's not perfect. It is driving us nuts, the fact that we see some little lag in our predictions compared to the observations, but it actually works pretty well. I don't want to say it works better than this model, it works better than the other model, for one reason. It all depends on the specific data set that you're using. We tried in New Zealand to look at a large number of beaches on east and west coast and trying to compare models that are very complicated, one like this, or simpler equilibrium models, or other models based that are data-driven, or simpler XGBoost type predictors. And the surprising and very annoying result was that it actually depends on the beach. Sometimes this algorithm is the best, sometimes Yates is still the best. You cannot say something definitive. You always have to work on your data set. That's why I'm always in favor of never running one model. Run a lot of models. Ensemble, decide after you have run a lot of models. Because we don't really have a theory that tells us for this data set, this will be the best algorithm. And probably there will never be that book. Okay, this is a shoreline example. There's another example that I want to present, and is the one from my friend and colleague Evan Goldstein. He goes around the world, collects sediment samples, analyzes them, and has developed this Instagrain camera. You put it on top of the sand, and within 1 second, it predicts the whole granulometric curve. So you can get all your parameters, the 90, the 50. I don't have here the picture, but the testing is incredibly strong. And I participated to all of this by standing up and looking at him while he was taking the measurements. So I contributed somehow. And of course, there are other examples. In COVID times, I joined forces with a colleague, and we decided that we wanted to actually produce music. At the time, I was a little bit in shock because my favorite pianist, Keith Jarrett, had some physical problems and could not play anymore. So I took all of the music that I had, we put it into we turned it into data, and from that we generated, using transformers, we generated music. Then I said, well, how do I know if this music is actually good? Here, I don't have a data set to test. So I called one of the most well-known pianists in New Zealand, Jonathan Crayford. He won for 2 years in a row as jazz pianist in New Zealand. I sent him a lot of files and I said, I want you to recognize when it's Keith Jarrett and when it's us. I have to say I was working with some pretty amazing two computer scientists that were really good because, for example, one of them was a pianist and said, hey, we need to put the effect of the pedal too, otherwise it will recognize it straight away. Okay, let's put the effect of the pedal too. And actually, at the start, when I started speaking, it was Keith Jarrett. At this point, it's AI. And the musician, the jazz pianist told us, I cannot tell when it switches from one to the other. I stopped it there because I thought what I was doing was ethically disgusting. And I said, okay, the curiosity, but I should stop it here. Little I knew that a couple of years later, there's now a lot of softwares that can actually produce music. And in fact, if you go to the website of my research group, you can actually listen to the Coast and Ocean Collective Blues, which is a tune that has been entirely generated by AI. It's a little bit cheesy, but it's okay, and for a laugh, it's definitely a good one. Okay, but the moment we deal with deep learning, we lose control of what we're doing, and that's always been something that has been worrying me, because I don't know anymore. I developed techniques to open up simple neural network to see which variable was doing what. But I cannot do that anymore with deep learning, too many parameters. So we decided that, and there's a new interesting approach, and that's PIM, physics-informed machine learning, in this case physics-informed neural networks. Now, this is where you constrain the behavior of machine learning algorithm with physics. I've seen incredible results, for example, in urban flooding. And we tried to do it again with this fantastic student, Eduardo Gomez de la Peña, to build a morphodynamic PIN to predict shorelines. The problem is that our theory for morphodynamics is not very strong. Our morphodynamics models, they can end up with mistakes that are really large. So we tried to couple our machine learning algorithm with the Yates model. And here are the results. Well, years of training is not so important. Here is the coupling. That's important. How strongly is the coupling? What is the role of machine learning compared to the role of physics, if we can call Yates physics? So the important thing is to look at this in this column. And what we can see is that machine learning alone, so with a coupling of 0, has a root mean square error in our prediction of shoreline position that is 4.3. If we use only Yates, the error is larger, but when we couple the two, there is a sweet spot where we actually improve predictions. But we are improving them by very little, not by a lot. I think we need some stronger theory there, but I think this is the future, where we constrain the behavior of machine learning with physics. Okay, we spoke already about two important fields, shallow and deep learning, and there has been a huge amount of papers here, so I think here you recognize your favorite saxophone player speaking with Lester Young and discussing how we're using machine learning. And I think that's an important discussion that we should always keep in mind, because machine learning has some incredible uses. I mean, if you code, I'm sure you're using Codex, ChatGPT, and one of those to debug codes. Debugging codes is honestly a different sport nowadays compared to when I was doing debugging. And so incredibly useful for sure. And the same if you want to generate emulators, machine learning will help you a lot for sure. The development, as I said, of mixtures between physics and machine learning is the area where probably we are going to make a real impact. And of course, machine learning can improve with new data coming in. We will get better by default because we keep getting new data. Okay, but that's the use. There is also the misuse of machine learning. Overfitting is a classic one. To get this figure going, it took me a lot of time to convince it to put the saxophone the other way around. Okay? and I would say in a lot of cases, we also have to ask ourselves, it has become part of my workflow. Do I need machine learning? And I wish I had this workflow earlier on, because when I started machine learning, I was so obsessed about learning about algorithms, using algorithms, that in a lot of cases, I didn't see that actually I could have used a multiple linear regression and it would have been maybe just as good. So sometimes we are misusing machine learning, especially when we blindly apply it beyond the field where the data is trained. You always need to have some validation of the model. Also, lack of interpretability means that we have to be careful on when we then use those models. Although my hope, I have to say, is that at some point, someone smarter than me will be able to open up also these deep learning algorithms and come out with the reasons why they perform this well. At that point, we will be generating also understanding, and at that point, I think machine learning really will explode. So, but we have uses, we have misuses, we also have abuses. As I said, if you use machine learning, deep learning, anything you want without validation, well, that's bad. That's bad. And let's not forget that machine learning is always and only dealing with data. So it's not a substitute for physics. It's not a substitute for understanding of processes. Real advances, for me, they remain anchored to theory. That's where real advances are. We can make wonderful predictions, but real advances are theoretical and will always be theoretical. Another big mistake is to trust your model so much that you ignore people that actually, maybe they know about that beach, and that knowledge remains important. Finally, if you use ChatGPT or similar to write the introduction of your paper, the literature review of your thesis, these are the perfect ingredients to see me screaming like hell. Because if you know how these algorithms work, you just cannot do it. The references that the algorithm puts into the text, they're never the most appropriate. Okay, now they fixed it, that at least these are references that exist. A couple of years ago, it used references that didn't even exist. Now they exist, but they're not the most appropriate ones in most cases. And sometimes they're wrong. The papers don't actually say that. This is definitely an abuse. So let's keep in mind all of this. Let's keep in mind also because now we are moving towards the final part of our discussion. And in this case, with AI agents, everything is changing. There is a big divide between shallow deep learning and what is happening now with AI agents. Because now our musician not only can improvise, but is listening to the band, is listening to the changes in rhythm of the drummer, is listening to the chords, is listening to the other musician soloing, and then, based on what perceives, acts and plays a music solo that is perfectly fitting with everything else that is going on. This change is huge. So let's have a look at it a little bit more. In this case, that's supposed to be me at work. So what are these AI agents? Because I think a lot of people still probably are not entirely aware. We have moved now into an area where we have entities, the agents, that perceive the surrounding, decide what to do, and then actually do it. That's a huge difference, because they have a goal and they will try to achieve that goal. And they can be just software, but imagine put them into robots or drones too. So they do this operation of gathering information, deciding what actions, and then interact with the environment. Now the crazy thing is that those agents have the ability to feedback. And the moment you allow for feedback, I think computer scientists are going in the direction of using multi-agents, because they hope the interaction and the feedback between the different agents will actually lead to even emergence of new things. That is actually quite scary. So they can handle very complicated tasks, I'll show you in a second, but agents will change the very nature of the interaction between students and supervisors. I'm afraid to say that students now have a wonderful supervisor in an agent. He's always there, fixes the code, decides, tells them where to get data that might exist and is available. But also, on the other hand, do we need PhD students? Here I'm talking from a purely drone-like perspective. Of course, we need students, and of course, students need advisors, but the relationship will change with agents. The projects that we assign to students will have to change. So I think they will affect our job, because they're not passive models that we develop and then apply. Now they decide on their own what to do. And they act. So yes, we are going in the Blade Runner direction. There is little doubt about that. So here's an example. Here's still me at work, together with Evan Goldstein. And there's Shoreshop 3 going on this year. And we told an agent, this is the prompt. Actually, we asked machine learning to write the prompt for us. What we asked was to go to the website of Shoreshop 3, get the data, develop a model, make the submission. We are literally not doing anything. We just wrote a prompt. Of course, we will do a little bit more. We're looking at the model to decide to develop, but the change is huge. And we wanted to build a big data set of shorelines. We just said, go out, get all the shorelines you can, and associated wave height. After 3 days, we had a data set of 11 million points. Again, without doing anything. This will change our job. I think I have little doubt about that. So let's begin to wrap up. And I wanted to have a slide about the future of coastal modeling. In my view, the future is hybrid models. We need to connect. We need to go ahead with theory. We should not leave that. We keep going with theory. We mix it with AI models. That's the best way, and that's how we can produce digital twins of coastlines that are valuable. Agents, in a couple of years, at the moment they are still a little bit clunky, they need complicated prompts. Hey, they've just appeared. In a couple of years, this will completely change the way we operate. And let's use it well, because one thing that we do bad in our field is that we run models and we make one prediction. Very deterministic. These type of tools allow us to explore uncertainty, and we should definitely do it. And we should definitely link these models to data simulation, because they will keep improving and get better and better. So, in my opinion, the future of coastal AI is physics-aware, adaptive modeling system where data and scientific insight play together. I'm almost done. A final summary. Machine learning is means focusing on not overfitting. A lot of algorithms. Every month there is a new algorithm. Understanding with this algorithm is we still struggle. We will get better. One thing I did not discuss is ethics of all of this. Is it really worth? Because we use a lot of energy when we train some of these models. So it's something to keep in mind. But it's definitely something we have to constantly discuss and get certainly better at. Finally, thank you, Dano. It's been a pleasure to interact with you. You have taught us a lot, and a lot more about modeling. Thank you.
Thank you, Giovanni. There's time for a quick question, one or two. Are there any pressing questions from the audience? No? Yeah? You were first, Jose.
Thank you, Giovanni, for this wonderful talk. I had a question. Could you elaborate a little bit on that coupling between physics models and machine learning or other types of models? At what levels you could do that?
So there are two levels at which you can build physics-informed neural network or couple machine learning and process-based modeling. The simplest way is to just do it with the optimization function, with the fitness function. And you just feed both algorithms there. And at that point, you choose which one is doing better, and every time you learn from one or the other algorithm. This is the simplest thing. In urban flooding, it's used also in a different way. They value a lot the predictions from convolutional type of algorithms, but then what they do is they also run the process-based model and they stop any nonsense that might come out from the machine learning. If the results are too divergent and too extremes from the machine learning, the so-called hallucinations, then the process-based stops it. And in urban flooding, this seems to be really the forward way. There's a third way of using all of this, and it's by embedding the physics inside the architecture. That's complicated to do. When we tried, things seem to invariably blow out, but I'm sure there are better ways of doing it, and there are some areas where they're actually doing it. So there are different levels at which we can couple physics and data-driven algorithms. I think that's the way forward.
Okay. Then I'll leave the other questions to the coffee break, I think. We'll move to the next speaker.